Good morning, everyone. Thanks for joining this session. Can you hear me? Yeah. Today, Andreea and myself are going to talk about rust-vmm, which is a recent project, and how we can build VMMs with rust-vmm. So first, one question. Who has not heard about Rust as a language? Paulo, of course. Of course. Okay. So I'm assuming everyone has heard about Rust, but a different question. Who has actually ever used Rust? Okay. So I was expecting this. So there's a majority of people here that has never used Rust. So I'm not going to make a presentation about Rust, but just a very quick introduction about why we're using Rust with rust-vmm, why we think it's a good language. And I just want to highlight one central feature of Rust, which is ownership. And ownership is a set of a small set of very simple rules about who owns the data that the Rust toolchain applies to each and every lines of your code. So with this, you can avoid, with Rust ownership, which is a very central feature to language, you avoid most of the used after free, double free, dangling pointers issues that you would find with other languages with C, for example. So Rust builds memory safety on top of ownership. And with ownership, you can also, because Rust prevents you from using data that you don't own, it also brings a much safer concurrency and multi-threading model. So with this simple set of rules, you get memory safety, and you also get concurrency safety. Last but not least, and the very good thing about Rust is that this is all enforced at build time. So it's not dynamic. It's not something that the runtime does. So there is no garbage collector in Rust. It's not a garbage collected language. So you get the benefits of safety, memory safety and concurrency safety without runtime overhead. Obviously, this brings some complexity when you actually write code. So you will find the Rust toolchain not being your best friend at the beginning, but eventually it becomes easier and easier. So why are we using Rust? I guess if you understood the ownership concept, it's kind of obvious. So if you try to map some of the main components and requirements from a VMM to the Rust feature languages, the Rust language features, it's kind of obvious. So memory safety, well, I guess a lot of the VMM components and features and requirements would benefit from memory safety, especially the memory model, the virtio implementation, for example. You have a safer concurrency with Rust, and well, with a VMM is typically a multi-threaded binary for vCPU, I/O workers, and you benefit from that as well. And again, well, VMM that doesn't bring latency overhead or a performance impact, so we also benefit from this from a VMM perspective. So that's why we believe that Rust is a very good language for building VMMs. So now, Andreea is going to talk about rust-vmm, the project.
Yeah. So I want to start with what rust-vmm isn't. And what rust-vmm isn't is not a product. So you are not going to take rust-vmm, compile it, and there you go, you can start VMs. This is not what rust-vmm is. Instead, you can look at rust-vmm as a collection of crates or a collection of building blocks. You just take what you need to build a VMM, but you will have to build your own VMM. So Rust provides virtualization components that are written in Rust, and they are called crates. So Rust packages are called crates. It's also open source, so you can find it on GitHub. Ooh, I'm nervous, I'm sorry, on GitHub. So why would we want to start this project? First, it offers faster development for new VMMs. So if you have a particular use case for a VMM and you want to write your own VMM, instead of starting from scratch, you can start from a set of already existing virtualization components. Each component in rust-vmm is very well tested. And we also insist very much on security because that is very important when you have multiple projects that are using the same components. And the third thing is that we want to provide a very clean interface. And by clean interface, what I really mean is that the interface needs to be flexible enough so that multiple VMMs with different use cases can use it. One of the projects that is currently using Rust VMM is Firecracker. I talked about it a bit yesterday. Just like one phrase, it's a virtual machine monitor, and it's super lightweight. And in Firecracker, we have this crate, which is called VM memory, that provides abstraction for guest memory. And in VM memory, you have a few primitives. So one of them is the guest address. Then you have a memory region, which is basically just a guest address, which represents the start of the memory region. And then in Firecracker, you have an anonymous shared memory. And then multiple regions in Firecracker represent, and anywhere else actually, represent a guest memory. And the memory regions are just represented as a vector of non-overlapping memory regions. So now this is very specific to Firecracker. So when we, and these are actually implemented with structures, so just structures with implementations. And when we moved this crate to Rust VMM, what we actually did is to convert all the structures to traits. So what is a trait? As Rust puts it, a trait is a collection of methods defined for an unknown type, self. But in other simpler words, trait is just an interface. So you can also call it like an abstract class, because it's an interface that can also have methods with default implementations which you can override. So now let's look a bit again at why we actually wanted traits. We wanted traits because the guest memory can be represented in multiple ways. So Firecracker just uses one of them, but then you can also have memory that is actually backed by a file. In Firecracker, this is not possible at the moment, so with a trait, you have the flexibility of implementing your own backend. And implementing your custom backend is not the only reason why you want to use traits in Rust VMM. Another reason is that even though we strive to have components that are independent, this in practice cannot possibly happen. So you will have dependencies between components. And one classic example is the dependency between the Linux loader and the VM memory. Linux loader is just a simple crate that just loads a kernel image into guest memory. So because of that, it obviously needs a reference to the guest memory. And now if you think about it, instead of actually depending on the guest memory implementation, you can just depend on a trait, which offers end users the possibility to use the Linux loader, but at the same time not depend on an actual implementation of the guest memory. So you'll see like in red, there is a trait called guest memory, and then a structure called guest memory mmap, which is basically an mmap guest memory. And then we have an implementation for the guest memory trait for guest memory mmap. And in Linux loader, you will see in red as well, that Linux loader does not implement on guest memory mmap, but it depends only on the trait. So let's talk a bit about the Rust VMM development process. People have ideas, we all have ideas, and in Rust VMM, from idea to an actual component, it's a bit, I don't know. Let's see. You first have to submit a GitHub issue. You have to describe your idea. You have to describe your component and why is it useful for VMMs in general and for Rust VMM. And then we start design discussions. All of this happens on a GitHub issue. Once we decided that this is a useful crate or component, we create an empty repository. The next thing is that based on the design discussions, we actually start submitting pull requests in order to have a useful crate or a crate in development. Now, from a crate in development to a crate that is actually published on crates.io, small pause, crate is a package, a Rust package, and crates.io is the Rust crate registry, so the place where you take crates from. So from a package in development to a package that is actually published, there are a few things that we want to do. So the first one is we want to make sure, as I said before, that the packages are very well tested. And we want to make sure that we have the same quality bar set for all the packages in Rust VMM. So what we do actually is we use the same continuous integration system for all packages in Rust VMM. And this needs to be set up before we actually publish the crate. Then we are really insisting on documentation because this is one of the problems that most projects out there have. And if you are going to use this component that you didn't develop yourself in your VMM, you really need to know how to use it. And this is where the documentation comes in, and documentation also has usage examples. Then we have tests. So there are like tests which are run for all crates and that can be run for all crates out there. But then we also have specialized crates that are depending on the implementation, so integration test and so on. All the crates in Rust VMM actually use dual license, so we have Apache or BSD3 clause. Currently, we have a few crates that are still in development. I'm not going to talk about each of them. I just wanted to give you a landscape. So there are we mostly publish crates that are bindings or that are offering wrappers over KVM and so on. Then we have crates in development. So these crates are they actually need more design discussions than anything else. So we are a bit slower there. And we also have empty crates, so the development didn't start on them. And I will let Samuel talk about how our project's using Rust VMM in practice.
Thanks. So how do we use Rust VMM? And before going into concrete example, I just want to describe who is contributing right now to Rust VMM. They're kind of the usual suspects. Red Hat, Google, Intel, and then we have AWS as well, and also Cloudbase, which is a small company who's contributing to Rust VMM for the Windows support. So they're trying to make Rust VMM crates work on Windows as well, and Alibaba is one of them. So those are the contributors. If you look at who contributes and uses Rust VMM, it's basically two entities, AWS with the Firecracker project and Intel with the Cloud Hypervisor project, which I will be talking about in a few minutes. So again, before going into more details on how you use those crates, how would you build a VMM from Rust VMM? The first thing you have to do is to decide which features you want your VMM to be using. I guess this is kind of what Paulo was describing before, where you decide you want a VMM that only does MMIO and no VFIO. You don't need hot plug. You don't need device pass-through. You select your features, and then from the Rust VMM crates, you're gonna cherry pick the crates that you need and merge that into something that looks like a VMM. So you can use functional Rust VMM crates directly from crates.io for those who are published on crates.io, or as a GitHub dependency, and I will show that as an example also later. Some of the Rust VMM crates are incomplete, or sometimes they're complete. People think they're complete, but they're missing one specific feature that you need. So you would fork those Rust VMM crate into your local VMM repo or some personal repo. And finally, Rust VMM is missing some crates for what you're trying to do. And you will have to implement those missing Rust VMM crates yourself and hopefully contribute them back to Rust VMM. And last but not least, you're going to glue all those crates together into the mysterious VMM glue code. OK, so let's take an example. We want to build a VMM based on KVM. We want to do device pass-through. We want to do PCI, virtio. So basically, we would pick all those crates from Rust VMM. Some of them, again, are complete. Some of them are not. And then add some glue code in there, and ta-da, you have a VMM. So what is the glue code I'm talking about? Just one example of the memory model that we have in Rust VMM and how you include that in your VMM. Basically, you're going to tell the Rust toolchain that you're pulling the code from Rust VMM directly. The VM memory is one example of a crate that is complete, functional, but not yet published on crates.io, so you have to pull it from GitHub directly. And well, in this example, we're going to use the mmap backend as a feature, because we want to do mmap-based memory. Then from the code, you're going to use specific features and expose structures and interfaces from the memory crate. And eventually, Rust is very verbose, so what we're trying to do here is just map some memory into a guest address space, create the mappings and mapping to add it to the guest address space. So we're just calling into the rust-vmm crates, API, and interfaces. Okay, so we have our VMM. Maybe we want to do a different VMM. We don't need PCI, we don't need pass-through, so we don't need VFIO. We just have to remove some of the crates, enable the MMIO transport for the virtio crates, and we have a different VMM. So that's the idea. And one example of how rust-vmm is used is Cloud Hypervisor, which is an Intel project, which is why I'm going to talk about this, because I work on this project. And you could call it the Cloud VMM, if you prefer. So it's KVM based, and we only aim at supporting KVM. And it's aiming at supported cloud workloads, and by cloud workloads we mean workloads that potentially can run in a private or public cloud provider infrastructure. We only support x86 for now, but we want to support ARM in the future. And since we want to support cloud workloads, we need it to be PCI based. We want device pass-through. We want migration, ACPI, vhost user, because we also going to follow we are following the split process model for I/O, etc. So which crates are we using in Cloud Hypervisor? We're using all the functional rust-vmm crates, so all the ones that we think are complete, and those ones, as Andreea highlighted, are all the bindings, the kernel bindings, the KVM, virtio, and VFIO bindings. We use the KVM wrapper, the KVM crate, which is a wrapper on top of the KVM ioctls. We use the rust-vmm memory model, the kernel loader, and the rust-vmm toolbox, which is the VMM CCUtil. Some of the crates in rust-vmm are incomplete, as I said. This is true for the virtio crate, for the device model. So we don't have yet a device model. The VFIO crate is also incomplete. So we fork them into the Cloud Hypervisor repo directly, and we complete it there, and we're trying to push our code back into the rust-vmm crate. And finally, some crates are missing from rust-vmm. We don't have a PCI crate in rust-vmm, so we have one in Cloud Hypervisor, and we're also planning to contribute that back to rust-vmm. And QCOW, the migration crate, which is a big deal, and a lot of the architecture-specific settings. So it looks very nice. Take those crates, put them together, have this very thin glue code, and yeah, very good. That's the expectation. The reality right now is a little different, because the rust-vmm is a young project, and we're still, as I said, we're still missing some crates. So if you look at Cloud Hypervisor as a project, the glue code I'm talking about, which is supposed to only be glue, it's still 40,000 lines of code. So we were hoping that this would be less, and the reason why this is 40,000 lines of code is because some of the crates are missing or incomplete from rust-vmm, and we have to implement that in Cloud Hypervisor. So looking at how those 40,000 lines of code are dispatched and shared across components is a good idea of where we should put our efforts in rust-vmm. So if you look at those 40,000 lines of code and where they are in Cloud Hypervisor, and you can see that more than a third of it is actually virtio and vhost code. So if we would be able to use a rust-vmm implementation for virtio, we would remove a third of the entire Cloud Hypervisor code base. Same for kernel bindings, which is that's even easier. So networking bindings, architecture-specific bindings. This is easier than implementing a virtio crate. So, and this is roughly a quarter of the entire code base. So that gives us an idea of where we should put our resources on rust-vmm, which crate we should work on first. And as a matter of fact, a couple of weeks ago, we had a rust-vmm meetup in Bucharest, kindly hosted by AWS. We had a lot of interesting discussion, and we decided to put our efforts in the short term on the device model and on the virtio crate as well. So if we, as Cloud Hypervisor, could use the device model from rust-vmm and the virtio crate from rust-vmm, we would basically divide our glue code code size by 2. And we're done. This is the GitHub organization for rust-vmm. If if you want to join, contribute, help, or use it, please come and help. Thank you. I think we have time for questions.
One question?
Thank you.
So besides writing a complete VMM this way, do you also envision the use case of having just the device backend as a Rust VMM use case?
Yes, actually we, yes, definitely. And this is, for example, in Cloud Hypervisor, we have vhost user device backend. And we're also aiming at when I was showing this chart of missing code, it was virtio and vhost, and we want to contribute that back to Rust VMM as being able to use the virtio crate and having an implementation for like a tab-based implementation for a vhost user backend. Yeah, so yes, there are different use cases. VMM is the main one, but you could implement device backend and maybe do a few other things. You could also envision to use like a memory model or virtio crate into something like QEMU if you're brave and willing to do that. I think Paulo wants to do that. Yeah. The FFI bindings for Rust are pretty good. So that's the easy part, yes. Right?
Okay, so thank you.
Thank you.
Thank you.